So, our next section, we're going to be talking about medians and altitudes of triangles. So, in our last section, we talked about mid-segments and what a mid-segment connected the midpoints of two sides. And it gave us some information. It told us that we had some parallel lines. It also told us that we had some relationships within our measures. So, today we're going to talk about medians, and it's also going to give us some relationships within our measures. So, before we even talk about our medians, we need to look at a couple of vocab words here. The first one, concurrent lines. This is where three or more lines intersect at one point. So, three or more lines intersecting at one point are called concurrent. That point where they intersect each other is called the point of concurrency. So, if you look at a picture, you've got three lines, at least three lines, it could be more, that are all intersecting at the same point. Those lines would be called concurrent. The point where their intersection is called the point of concurrency. So when we talk about the median of a triangle, first of all, we have to know what does that do. The median of a triangle connects the endpoints, or the endpoints of the segment, rather, are the vertex of the triangle and a midpoint of the opposite side. So it's going to connect one of the vertices of my triangle to the midpoint of the opposite side. That is a median. Now, if we know anytime we've got a midpoint, what else are we going to have?
Mid-segment.
Now, you could if they're being connected.
A vertex.
Not necessarily.
A line.
Well, if we've got a midpoint, we know a midpoint does what to a segment? It splits it into two pieces, right? And what do we know about the two pieces? Yeah, they're going to be congruent or equal, okay? So, if we've got a midpoint, then we know that we've also got some congruency. So, if you look at your picture here, we know that segment BD is a median of triangle ABC. Within a triangle, there are three medians total, each vertice connected to the midpoint of the opposite side. So you've got three medians that can be drawn in each triangle. Where all three of those medians, they're going to meet at exactly one point, so they're concurrent to each other. That point of concurrency or point of intersection for my medians is called the centroid. So where all three of my medians are crossing each other, that's the centroid. So if you look at your bottom triangle here, you've got medians PT, you've got medians QU, and you've got median SR. Those are your medians. How do I know they're medians? Good. The tick marks there are telling me that T, S, and U are midpoints of each segment. So if they're connecting a vertex to a midpoint, we know we've got medians. So where are all three of those medians crossing each other? At what point?
V.
At V. So V is the centroid here. Alright, so from our activity that we just did, we just concluded what our concurrency of medians theorem says. Okay? It says that my three medians are concurrent at a point, and we know that point is called the centroid. Okay? So what this theorem tells me is that the medians of a triangle are concurrent at a point, and we know that that point is called the centroid. Okay? It is 2/3 of the way from the vertex to the midpoint of the opposite side. Okay? So if we're looking at this picture, C is the centroid. So that would tell me from D to C, which is your longer piece, is 2/3 of the entire median. So what do I know about from C to J? It's what? 1/3. Good. And if I'm looking at E to C, it's 2/3 of the entire median from E to G. So what about C to G? It's 1/3. And then from F to C, that's again the longer piece of your median, F to H. It's 2/3. So what do we know about C to H? It would have to be 1/3. Good. So we also noticed that there was a relationship between my short pieces and my long pieces of the medians, okay? So we said that we noticed that the long piece was double the short piece, and opposite of that, the short piece would then be half of the long. And so if we're looking at our picture, I know that DC would have to be double whatever CJ is. I know that JC would have to be half of whatever CD is. So there's a relationship that I can look at between those parts of my medians that can help me figure out the lengths. So in the first example, it's telling me in triangle ABC, D is the centroid. DE is 6, and it wants me to find BE. So first of all, let's label what we know. So D has to be the centroid. Now, how would I know that D was the centroid even if it didn't tell me?
Because it's in the middle. I don't know if that's how you play it.
That's part of it. It is in the middle. That does help. But what is intersecting at that point, D? Each one of these segments, what are they called?
Mid-segment. Which segments?
So, since we know that all three of those segments going through my triangle here are medians, we know that D, where they're intersecting, has to be the centroid by definition. Even though it didn't necessarily have to tell me that, I could know that because I know by definition. Okay? So, from D to E is 6. So, let's label that. That's this piece down here. And I'm looking for the whole piece B to E. So what other piece am I going to have to know? What other piece am I going to have to know before I can find the whole thing, B to E? Yeah, I'm going to have to figure out what D to B is. So any ideas on how I can find that?
Tape. It'd be 6 on there.
It wouldn't be 6, but I'm going to have to do something with my 6. I agree.
You have to times your 6 or divide it.
Times it by... Because BD is the long piece, right? And so that means it's double the short piece. Well, DE is my short piece. So I need to take DE and times it by 2. So what am I going to have here?
Is that DB?
Yes.
Okay.
So what is DB? Or BD, either way you want to call it. What is its length? 12. Is that my final answer? Nope, because it asked for the whole thing. So now how could I figure out what B to E is? Yeah, add them together. That's way back from Unit 1 that tells me if I've got one whole segment being split into 2 pieces, add the 2 pieces together to give me the whole thing. So we know that to get B to E, I'm going to have to add ED and DB. And so what's that going to give me total? What does BE have to be then? 18. M is the centroid of triangle WOR, and WM is 16. Find WX. So let's label. W to M, that's your long piece, is 16. And I'm looking for the whole thing. Ideas.
Divide 16 by 2.
Okay, divide 16 by 2, and that's going to give me which piece? Good. MX, if I take half of 16, or divide by 2, then it is what? What's MX going to be? 8. So now, how do I get WX? Yep, put those together. 16's the long piece, 8's the short piece. Together, they're going to give me what? 24. If XA is 8, what is XB? So if XA is 8, so that's this piece, then what is XB? So ideas.
Divide 8 times 8 by 2.
Good. Divided by 2, and that's going to give me my little piece from A to B. So A to B is half of 8, which is what? 4. And then how do I figure out XB? Add them together. So 8 plus 4, which is total of 12. Good.
I quietly said that before.
All right. So the altitude of a triangle, this is our last piece here. Altitude of a triangle. It is a perpendicular segment from a vertex to the line containing the opposite side. So if you look at this picture of your triangle, AD is an altitude there. Now, just like with our medians and our mid-segments, there are a total of 3 altitudes that can be drawn, connecting each vertex perpendicular to the opposite side. Now, notice in this picture that altitude is inside the triangle. But know that the altitude could lie on the triangle and be a side of the triangle. For instance, if you have a right triangle, this piece is your altitude. You could also have an altitude that falls outside of your triangle. And that's if you have an obtuse triangle. And I'm taking the altitude from this top point. It's going to fall outside of the triangle. Keep in mind another point for altitude is also height. So if you're talking about the height of the triangle, you're talking about the altitude. Now, again, all 3 altitudes can be drawn in, and when they do, they're all intersecting at one point. That point of concurrency is called the orthocenter. So if you're looking at your bottom picture there, O is the orthocenter. So in our last example, you're just determining, are these segments medians, altitudes, or neither? So if I'm looking at S to T, median, altitude, or neither?
Altitude.
Altitude, and how do you know?
It's going straight up.
Good. It's making a right angle with that side, so it is an altitude. All right? What about UW? Here's UW.
Medium,
It's a median, and how do you know it's a median?
I guess.
How do you know it's a median?
In the middle.
Good. It touches the middle of W, and we know it's the middle, or it touches in the middle at W. We know it's the middle by my congruent marking, so it is a median. In the last example, it's talking about KX. It wants to know if it's a median, altitude, or both. Well, KX is making a right angle with the third side, making it an altitude. But we also realize by my congruencies that X is a midpoint. So therefore, this would both be an altitude and a median.